In this video, we are going to discuss few problems on sampling theorem. From sampling theorem, lots of problems are coming in GATE exam and other competitive exams. So in this video, we'll try to understand how to find Nyquist sampling rate for certain signals. So this kind of problems are coming regularly. Let us start. So this is the first problem we'll tackle. And similar kind of problems, few more problems we'll be discussing. But before that, just a quick review of sampling theorem should be there. Okay, let us consider this thing very briefly. So if one signal xt is given, this is a time domain signal. So it will have certain frequencies, and if we use Fourier transform, then we'll get its spectrum. Suppose this signal, this is a time domain signal, but this is now I am considering spectral, and it is band limited. Maximum frequency is B Hz, and this side minus B Hz. So I'll call that this from 0 to B, this is the bandwidth. So signal xt is band limited signal. Now this is a continuous time domain signal. Just I am going for one signal. So this is time axis. This is your x of t. Now, if I take samples on this, I can take sampling at a regular interval. So, what I will get? So, I can take samples at regular intervals. Suppose that interval is Ts. So, Ts, 2 Ts, 3 Ts. There I will take samples. So, this is the amplitude. This is the amplitude here. This is the amplitude here, like this. So those amplitude, if I consider only at Ts, 2 Ts, 3 Ts, like that. Okay. So these are the sampled version of this. I will call it XST. So it's a discrete sequence. Okay. Just at t equal to at Ts we are having one sample, at 2 Ts we are having samples. So this kind of discretized in time domain we can go for. This process is called sampling. Now from this sampled version of this signal, we can get back the original signal. So from this XST we can get back. Just if I use a low pass filter, if I pass it through a low pass filter, we can get back this envelope. So this envelope, this one, it's the envelope. So this envelope we can extract here. Okay, we can get back exactly xt signal. So what is the condition so that we will be able to extract this xt signal through a low pass filter? And what will be the cutoff frequency for the low pass filter? So from here questions are coming. So you can see that whenever we will take a sampling, so this is the spectral for xt, I will call it capital XF. Now what is the spectral for capital XSF? Okay, that you need to understand. So this is the F, right? And this is, there I will plot it capital XSF, the spectral of the sampled version. What is happening? If Ts is the sampling time, then the frequency Fs I will call it 1 upon Ts. Okay, there is sampling frequency in Hz. This is in Hz. So if we go for ideal sampling, then at 0, at Fs, at 2 Fs, like that, all those integer multiple of Fs, there the spectral will repeat. This xs will x of f will repeat. So at 0 this was the spectral. This is b and this is minus b. At fs again the same spectral will repeat. So this will be fs plus b. This is your fs minus b. Similarly here, even in left side, minus fs minus 2fs, same thing will happen. Okay, so you will get a periodic things. Okay, whenever you will take sampling. That theory I am not going. I have made videos, so you can go through that one. But to solve the problems, this is not required. Just try to understand what I am saying. Okay, so whenever you are taking sampling at regular interval Ts, in spectral, what is happening? It is becoming periodic. At Fs, 2Fs, 3Fs, the same spectral will repeat. So this is the overall spectral of XSF. Now, if I want to extract the signal, I need to use a low pass filter with this bandwidth. Okay, I can go for this one, so different color. So if I consider one filter to select only this part, then it is sufficient. We will select only this band and rest band will be rejected. So this is your low pass filter. Then we will be getting the same spectral as this one. So its corresponding time domain will be same as xt. So we will get back the original signal. So no distortion, nothing is there. But for that, what is the requirement? Requirement is that we should have sufficient space here, okay, some gap here, so that these two ends, they should not overlap. Okay, then I can use a low pass filter to select only the spectral around the 0 frequency, and this Fs should be more than B. Sorry, this cutoff frequency, this omega low pass filter cutoff frequency Fc, that Fc should be obviously more than B, but it should be less than this part. Okay, it should not accept this part. Okay, now before that, so when these 2 points will not coincide or will not overlap. Okay, if this part Fs minus B is more than B, then it is sufficient. So what is the condition? That there is no aliasing, okay, no overlapping. So this Fs minus B, this point should be right side of this point. This point is B. So what is the meaning? The Fs should be more than 2B. So I can put equal sign. So this is your sampling theorem. It says that if we take a sampling for a signal, if sampling rate is more than 2B, Fs is more than 2B, then we can get back the original signal through one simple low pass filters. Okay, this simple sampling theorem, and this minimum rate, F minimum sampling rate is called the Nyquist sampling rate, that is 2B. Okay, so I need to understand what is the bandwidth of the original signal. If I take double of that bandwidth, I'll get Nyquist sampling rate. That's simple. Okay, now with this concept, we'll try to solve the problems. Okay, it's not very difficult. If you understand Fourier series, Fourier transforms a little bit, you will be able to solve it. Okay, right. Now consider the first problem. Now what is the signal here? The signal given here, this is, okay, just see, what is xt? Xt is given cos 6 pi t. This is a periodic signal. Another one is, another component sine 8 pi t. Okay. So what is the frequency of this one? So it's a periodic signal. So cos omega t or cos omega t, that we can write cos or omega ct is 2 pi fct. Here omega c is the radian per second, angular frequency, and fc is linear frequency, it's in hertz. Okay, so if we compare these things, 2 pi with 6 pi, 2 pi fc equals to 6 pi, so obviously fc equals to, here the frequency f1 I will call it, equals to 3 hertz. Can you compare these two? So 2 pi into 3 will give you 6 pi into t. Okay, similarly here, this signal sine or cos does not matter. Okay, the same form. So its frequency will be f2 equals to, so I'll divide by 2 pi here. So 2.85 by 2 pi is 4 hertz. Okay, so this signal contains two frequency. One is 3 hertz, other one is 4 Hz. So what is the maximum frequency? So if I consider the spectral, then it may look like that. At f1 I will have one impulse kind of things if I go for Fourier transform. Another impulse I will be getting, so this is at 3 Hz. And again at 4 Hz I will be getting another impulse. Okay, so I am not going for exact configuration. So this is real, this is imaginary. So that I am not going for. But we are having two frequencies. One is 3 Hz, other one is 4 Hz. That's all. So what is the maximum frequency? Maximum frequency is up to 4 Hz. So this is the bandwidth we can consider. So bandwidth equals to 4 Hz. Maximum frequency is 4 Hz. That's there. So if for this signal, if it is the xt, the Nyquist sampling rate will be simply double of that. So sampling rate for xt, okay, the sampling rate fs for xt will be how much? 2 times of 4, that means 8 Hz. That's simple. But question here is given the sampling rate, Nyquist sampling rate for yt, okay, where yt is given as, so this is little bit tricky, x of 2t plus 5. Okay, so what is happening here? So this addition of a constant, it is a time shift. That will not give you any frequency change. Frequency will remain same. If signal is translated, so its shape is not changing. Okay, frequency content is not changing. Could be this phase is different. Okay, but magnitude spectral will remain same. But when something is multiplied with t, that will give you, and if it is more than 1, it is a compression. Okay, so 2t means the signal is compressed little bit. In time domain, if it is compressed, in frequency domain, it will be expansions. Okay, that is a simple idea. So this is the compressed signal. This alpha t, this is 2, this is a compressed. Why? Because this alpha is more than 1. The constant that is multiplied with t, that factor is more than 1. That's why the time domain it is compressed. So in frequency domain it is expansion. So in time domain it is compressed by 2 factor 2. So in frequency domain it is expanded by factor 2. So what will happen? Its frequency will become double. Okay. So if I replace t by 2t, you can see that x of 2t. So this t is replaced by 2t, everything will become, so 6 pi t will become 12 pi t. This will become 8 pi t will become 16 pi t. Okay. So this yt will have two frequencies. Which two frequencies? Double of this one. One is 6 Hz. And this one will become double of this one. It's 8 Hz. So it will contain these two frequencies. So what is the maximum bandwidth? Maximum frequency is 8 Hz. So what is sampling rate? So sampling rate should be double of this maximum frequency. Is 2 times of 8. Means 16 Hz. That's all. Okay. So this is the key idea, that whenever something is t alpha t, x of alpha t. So this is important. X of alpha t plus beta, this kind of thing. So beta is for translation, time shifting. So for that there is no change in magnitude spectral, but alpha will give you some change in magnitude spectral. So if alpha is more than 1, it is compressed in time domain. In frequency domain, it is expansion. So in frequency domain, it is a multiplied. Okay, this alpha times, like that, it is 2. This is becoming multiplied by 2, it is becoming 6. This 4 is becoming 8. That's all. So this is true not only for periodic signal, it is also true for aperiodic signal. I hope you have got this point. Okay, so we can move for the next problem. So this one. So this is the next problem. We need to find out Nyquist sampling rate for this signal st Okay. So ST is given as, try to understand this one. This is sine 500 pi t upon pi t. This one form multiplied with another sine 700 pi t over pi t. So this is a product of two signals. That's simple. Now to get the idea of this thing ST, so we need to find out, we need to understand the bandwidth of this signal. If I can find out the bandwidth of this ST, then job is done. If it is V Hertz, then sampling rate will be 2B Hertz. That's all. So how to find the bandwidth of this signal? Okay. So what you will do? So first, this is product of two signals. So this signal, what is this signal? This is a sinc function. This is another sinc function. So these two sinc functions, they are multiplied in time domain. Remember, whenever they are multiplied in time domain, in spectral domain will take convolution. Okay. So this is small st. So it's capital. So we need to understand capital S of f. What is this? What is the bandwidth of this spectral? That we want to understand. Now, what is the bandwidth signal spectral of this sinc function? Okay. Very easy to understand. Try to understand this thing. What is the meaning of this one? So sine 2 pi fct upon pi t. If it is of this form, okay, it's spectral, this time domain. Its Fourier transform, if I go forward, then it will look like that. It's a flat spectral, it will give you from starting from 0 up to the frequency, this frequency fc. That's all. So if I have only sine 2 pi fct, it's a pure sine wave, periodic wave, it is having a single frequency fc there. But whenever you will multiply by 1 upon pi t, what will happen? You will get a continuous spectral from 0 to fc, a constant one. And beyond that, it is 0. Similarly, this side, minus fc. So left side is sinc function, right side is a gate function. So if I consider a sinc function, so these functions, it would look like this way. Okay, that I am not going to discuss here. So if I take Fourier transform this one, I'll get this kind of window function. Okay, so what is the bandwidth? Bandwidth is this thing only, fc. Okay, so I have two components, these and this. So in SF, we'll take convolution of these two, right? So this signal, so this fc, what is the fc for this one? fc1 I will call it. So it is, same thing, it's a 2 pi, I'll divide by 2 pi, 500 pi by 2 pi, it will be 250 Hertz. And what is the frequency for this one? This frequency, fc2, it will be 700 pi by 2 pi, 350 Hertz. Am I correct? So what we will do? We will go for this thing to get this thing, capital SF. This is our task. So what I will do? The first signal is this one, first component rather, it is up to 250 Hertz, is minus 250 Hertz, and we need to take convolution with the second component, and that is a little bit wider. It is 350 Hertz, it is minus 350 Hertz. So this is the AF, frequency domain. Okay, this is the first term. Okay, so if I consider x1, so capital X1F, and this is your capital X2F, right? So I need to take convolution. If you take convolution, simply that, so to get function, if I take convolutions, I will get trapezoidal signals. Okay, that is not very important for us, but okay, that thing also I have discussed in my video. So I'll be getting this kind of trapezoidal waveform. But main important thing is that, so this zero frequency, this is the zero frequency, addition of 0 plus 0 is 0, and this one just you can add. So 250 plus 350, so maximum will be 600 Hz. So this end will be your 600 Hz. Okay, so if you want to understand exact one, so this minimum of these 250 and 350 is 250. So this will be your 250, and this will be 250 less. Okay, so 600 minus 250 is how much? Okay, I think it is 350, right? So this will be the spectral in positive side, F. Similarly, you will be getting in negative side. Okay, so what is the bandwidth of this? This is your overall signal SF. So bandwidth, maximum frequency is 600 Hz. This is very, very important. So in short, what you will do? Just find the frequencies. I come to this point. Just find the frequency of this one, this sine wave, if it is there. This is 250 Hz. And for this one, 350 Hz. If it is multiplied, just add this 2. 250 plus 350 will give you 600. So what is sampling rate? So sampling rate Fs will be 2b, means 2 into that 600, means 1200 Hz. Okay, so option C is correct. So this problem appeared in GATE ECE 2010. So these kind of problems are regularly coming. Okay, so don't worry at all. So it's very simple. You can solve it very quickly. Okay, so okay, I can give you one more problem. Suppose if I consider this thing, xt equals to sine 40 pi t upon pi t, that whole q, times sine 10 pi t upon pi t whole square. Okay, so what is the, for it looks complicated, but it's very, very simple. Okay, how to tackle these things, right? So what is the frequency of this one first? This frequency is simply 20 Hz. Can see 40 pi by 2 pi, you can 20 Hz. And for this one, what is the frequency? It is the 5 Hz. It's fine. But if you take this power 3 times, means 3 times multiplied. So frequency of this signal, first signal, okay, this x1, if I call this is x1 t. So this x1 t, its spectral will be 3 times of that, because we will be taking multiplication 3 times. So 3 times addition, 20 plus 20 plus 20. So 3 times 20 means 60 Hz. Okay, and what is the frequency of this one, this x2, with square? Okay, so this x2 signal, its frequency will be 2 times, because power is 2, it's a 2 times of that, 2 times of 5 equals 10 Hz. Okay, now again it's a product of these 2. So what I will do? So xt, what is the frequency? Frequency will be addition of these 2. So 60 plus 10 is 70 Hz. So 70 Hz is the maximum frequency of this signal xt. Okay, so what is the sampling rate? Will be double of that, 2 into 70 means 140 Hz. Okay, so any problem could be solved in a second. So remember that. So this power you should multiply with this one. This power should multiply with this one. Then at the end we should take addition of these 2, because we are having multiplication. Okay, clear? But be careful, if it is a convolution, just we need to take maximum of these two. Be careful. Instead of this one, if I say, suppose I'll take different color, this is a convolution between these two. Okay, means xt equals to x1t convolution with x2t. Then what I'll do? I'll take maximum frequency of these two. Because in spectral domain, it's a multiplication. So which will be having maximum frequency? That will be there. So its frequency is 60, it's 60, it is a 10. So xt will have maximum frequency only 60 Hz, not 70. Don't add. Okay, if it is taken convolutions. Just take the maximum frequency, this one. Then sampling rate will be double of that. Means 2 into 60 equals to 120 Hz. Okay. I hope it is clear. Okay. Now take one more problem. This one. This is hard problem. Can you see this one? So we have two real valued signal xt, that is band limited minus 500 Hz to plus 500 Hz, and yt, another band limited signal, minus 1 kHz to plus 1 kHz. Now zt is given as product of these two. Okay, so it is very simple. Already I have discussed these things. So what I have said that xt, so this one xt given as is sampling is minus 500 Hz to 500 Hz. Okay, and yt is minus 1 kHz to 1 kHz. Right? So what is the maximum frequency for this one xt is 500 Hz. What is the maximum frequency of this one? 1 kHz, means 1000 Hz. Okay. So now zt is the product of these two, xt multiplied with yt. Remember, this is a product. It's a multiplications. Okay. This is multiplications. Then what is happening? So total maximum frequency of zt will be, so f max in zt will be how much? This 1000 plus 500. It means 500 plus 1000 means 1500 Hz. So safe doesn't matter. Okay, xt can have capital XF can be like this, up to 500 minus 500, and this could be something different, like this. This is your 1 kHz, this is minus 1 kHz, doesn't matter. After taking overlap, taking this convolution of these two, we will have a spectral up to 1500 Hz. So safe could be something like that, does not matter for me, but it will be limited within 1500 Hz. Okay. So what is the sampling rate? Fs will be double of that, 2 into 1500 means 3000 Hz, and 3000 Hz means 3 kHz. So answer should be in kilohertz, so it should be 3 kHz. So this problem appeared in GATE ECE 2014. So these kind of problems are regularly coming. Okay, I'll solve more problems, so keep watching. Okay, in this channel we'll be solving lots of interesting problems. Okay, so if this is interesting, so then you can just press a like button and you can share it to your friends. Okay, thank you, thanks for watching. We'll discuss more problems in other videos.